So welcome everyone to the Performance and Capacity stream. My name is Piara Bamra and I'll be chairing this session. We're very pleased to have Peter Enrico from Enterprise Performance Strategies, and he's going to be presenting on coupling, facility measurements and tuning recommendations. We're going to have some time towards the end to ask Peter any questions, but if you want to ask any questions as they come up, please do feel free to ask them using the chat box. And at the end, if you do prefer to speak instead of typing the question, then just let me know so I can unmute you. As with all of our sessions, we would appreciate if you could leave us some feedback at the end as well. And I'm going to put a link in the chat box so that you can direct yourself to that link and leave us some feedback. It always helps us make these conferences better each year. I'm now going to hand it over to you, Peter, to start the presentation.
Thank you very much. Good afternoon, everybody. I hope you're all having a good day. My name is Peter Enrico of Enterprise Performance Strategies. And today what we're going to do is we're going to talk about coupling facility, measurement, tuning, hints, and tips. Now, as you can imagine, the coupling facility is a huge subject. So what I've done here is I think I've selected some key areas of interest. And the reason I chose those areas, which you'll see in a moment, is not just because of the performance benefits. If you understand the measurements, it can take some tuning action, but it'll teach us something about the coupling facility. So I kind of selected an area related to lock structures and cast structures and some other stuff. So it's a nice rounded presentation, and I hope you enjoy it. Just a couple of things first, real quickly. This is one of the things we do is we also do education. So we have some educational webinars coming up. So if anybody's interested in taking some online educational webinars, it's like this. We're going to be presenting like this, but we have our Essentials Performance Tuning class, which is taught by my colleague Scott Chapman, about I/O, storage, CPU, and pricing and things such as that. There's a Parallel Sysplex class, which is a 2-day class, which goes into much more detail than this presentation does, as you can imagine. And then we have a WLM Performance Reevaluation and Goals workshop, which is everything workload manager in a week. And just to point out, one of the things that I will say is that one of the interesting things about the workshops is before the workshop, you send us data, and then in the workshop, you're going to be analyzing your own environment. So it's not just a week of workshop, it's also a week of you doing an actual productive analysis. So think about them. The other thing I just want to point out is we do these regular free half-hour webinars every 2 weeks. So if you're ever interested in a educational webinar every 2 weeks, it's only a half hour. In fact, what we do is we present it for a half an hour, and then we open up the phone call to anybody who has any questions about any subject. And this is our, I guess our agenda for the last few sessions, which I call the fall 2022 and the winter 2023 sessions. And these are the sessions we've already done. All the sessions are still available online if you're interested in seeing past sessions, but these are the sessions for the future. So come to our website, sign up for the educational webinars. If you attend, you attend. If you don't, you don't, but it's a pure educational thing for a half an hour with a Q&A, and feel free to ask us questions. And then finally, if you like what you see, just remember what I do for a living is we provide SMF and decollect and other types of data reporting services. So if you're looking for something to report your SMF data, that's exactly what we do, and it comes with analysis, and there's lots of things going along with it. We also have a free offering if you're ever interested in the free version of our product. So certainly feel free to contact me or contact our website via these links in this presentation. So let's talk about the coupling facility. Now, as I said, this is going to be coupling facility measurement, tuning, hints, and tips. And the first thing you have to understand to basically understand anything to do with the coupling facility, anything to do with measurements, tuning, and capacity planning, or whatever, is to understand the flow of a request and how that is affected by different areas in terms of performance, how the performance is affected by different areas. So what we're looking at here is a very simplified view, a very high level 10,000 foot view of a coupling facility environment. You have some machine. Now I'm only showing one machine here, but of course you can have multiple machines, multiple KEKs. And on those KEKs, you have one or more LPARs that are exploiting a coupling facility for coupling facility structures. Remember, all a coupling facility really is an area for us to have what we call a shared area of memory to allow multiple systems to coordinate their processing again, with each other. So on the left-hand side here, we have our ZOS systems, and on the ZOS systems, you're going to have a requester. Now, what a requester is something that's going to be exploiting a coupling facility structure. A requester could be DB2, it could be XCF, it could be RACF, it could be, there's so many things that exploit coupling facilities. So as a result, you're going to have these requesters. And it's the requester, of course, that is actually making the request to the coupling facility. Now, the requester, when it makes a request to the coupling facility, meaning a structure, it never talks to the coupling facility directly. Instead, what happens is it communicates with a component of the operating system called XES, or SES, they call it. And what XES does is it's responsible for the interface to the coupling facility. So the requester makes the request, it goes to SES, and then what SES does is take that request and eventually passes it off to the coupling facility, which then at that point basically becomes a hardware request. And the first thing it needs is to stage that request in what's called a subchannel. So you have so many subchannels, and I'll go into that in a little bit more detail. And think of the subchannel as being a software staging area for the request that eventually is going to be made over to the coupling facility. Once the request has a subchannel, it then needs a channel, a coupling facility link, in order to communicate from the ZOS system over to the coupling facility itself. So once you have the subchannel, the next thing that the SES has to do is stage the request in a coupling facility link, which eventually then makes that request over to the coupling facility itself. So this is a physical link, or it could be a memory link, which is the whole big discussion, not a big discussion, but just understand that your coupling facility could be a separate physical machine than your ZOS system is running on. So it's going to have a wire between the two of them, the coupling facility link, or they could be on the same physical box, but you're going to have a memory to memory link. Just the point is it's a link. That's the main point of exercise logically. Once it goes into the coupling facility itself has some number of structures. And again, all a structure is a control block in memory. So think of these structures as shared areas of memory. And we have list structures, lock structures, and cache structures. And each one are meant for different reasons. A list structure is meant for queuing. It's meant for looking at records and things like that. A lock structure is meant for serialization. And a cache structure is just that. It's really basically two main functions for a cache structure, which is caching the data in the coupling facility so you have better, faster access than doing an IO out to the disk. Or what it also does is what's called buffer validation, which we'll talk about towards the end of this presentation. And what buffer validation means is to make sure that you always have the most recent version of the data, because the data can be shared amongst multiple systems. You always want to make sure you're acting against the most valid version of the data. And on the coupling facility, you have the structures, and they're in memory. The coupling facility itself has some number of processors. So you have the physical CPU capacity that needs to be thought about, and that's going to process the request. Once the request is processed, it's actually sent back over to the link, which is then sent back over to SES, and the requester is going to get its answer. So what I just did there was I just described at a very high level what a coupling facility request does. But let's look at this from a performance point of view. And I'm not going to go into all these areas in detail during this presentation, but what I do want to do is kind of give you a flavor of the different performance areas or stages of performance that you have to be concerned with when measuring or tuning a coupling facility. So going back to what I just said, you have these requesters who are making the request to the coupling facility. Some things you're always going to want to know is who are the requesters? How are they making the request, which I'll talk about in a moment, because we have something called synchronous request versus asynchronous request. How many requests are they actually making? Are they just making a few requests? Or are they making millions and millions of requests? And how are they affected, or what workload is affected by poor performance from the coupling facility by the requester? Now, when the requester makes the request to SES, we're going to see in a moment that it makes the request to synchronous and asynchronous. And what SES does is some massaging of these requests so that perhaps if it sees a synchronous request, it may convert it over to asynchronous. And the question is going to be why, and how is that going to affect the performance of the workload? Or another thing that SES does is sometimes batch the requests together. So even though the requester may be making, 1,000 requests, those 1,000 requests might end up being one request to the coupling facility. So we kind of want to know that that's going on. Then when I said we have the subchannel, which is a software staging area, and you only have X number of subchannels per link. So because you only have so many subchannels per link, you can think of the subchannel as being a performance bottleneck if you don't have enough subchannels. You can imagine that if a requester tries to get, tries to make a request to the coupling facility and all the subchannels are already occupied and being used, you're going to have what's called subchannel busy, which of course is going to delay the workload. Eventually, you're going to get the path. This is the link itself. So you only have so many links, which is usually far fewer than the number of subchannels. So naturally, if you only have so many links, you're going to have what's called path busy. In addition to that, you got to remember that the request has to go from the from the requesting ZOS system over to the coupling facility. And this link has distance. So there's going to be some delay that's going to happen over the link. Now, if it's a memory-to-memory link, it's going to be quite quick. If it's a regular coupling facility link, you have short distance links, you have long distance links, you actually may be going over a long distance. And you got to think to yourself, if the coupling facility is maybe, let's say, 10 kilometers away from the ZOS system, that 10 kilometers, it's going to take time for the request to go across, which is basically the speed of light. So what's going to happen is it's going to have some amount of delay. So I want to understand that delay as well. So how many requests are being made over to the link? Are we getting link busy? What's the response time and the technology of these links? Because they could be a gating factor in adding to performance. And as I said, in addition to things, we have these coupling facility structures. So the structures themselves have certain performance points. And I'm not going to go into all of them in this presentation, but I am going to talk a little bit about the lock and cache structures and what some of their performance points are. But just know that you're going to have to tune the structure itself, because the way the structure interacts with the request may impact the performance negatively. And if you tune it, of course, you want to improve it. Of course, we have process, so we want to understand if we have enough processor capacity. And overall, we're going to send the request back out to the requester. So we're going to be interested in the overall response time of the request. And this diagram gets that much more complicated if you're duplexing structures, which I'm not going to go into right in here. But the point is just understand that all along the way of the request, you have a series of performance points that we need to always look at, and just be aware of that. So typically when I do a coupling facility analysis, I ask myself a series of questions. In the class, we go over what these questions are, but I break the questions up into these primary categories. So these are what I'm listing out on this particular slide are the different areas you always need to be measuring, you always need to be understanding of, and you always need to be looking at performance and possibly tuning. So there's something we call the host effect, which I'm not going to go into in this presentation. But what the host effect is what is the cost in terms of CPU? What is the cost to ZOS to make a coupling facility request? Many people are so concerned about how busy the coupling facility is. That's not as interesting as you might imagine as how many CPU seconds are spent on ZOS to do the coupling facility request, because those are true MSUs that are being included in tailor fit pricing or peak of the month. So what is that CPU cost? So that's a whole presentation of itself. I don't think I go into it in this presentation, but we always want to know that. And structure intensity is basically which structures are impacting performance the most of my environment. You always want to be aware of your configuration. You want to be aware of your subchannel and link loads and utilizations. As I mentioned, you might be busy on the subchannel, you might be busy on the link. You want to understand how busy these things are, if you need more of them, better technology. Of course, you want to understand the processor configuration and how busy your CPU is. So even though the CPU busy on the coupling facility is not as interesting in how much CPU is being consumed on ZOS, we do want to understand the utilization, because technically speaking, you could have a processor bottleneck or something like that, or too busy on the processor. Of course, you want to understand storage, how much storage these structures are occupying. Do you have enough for recovery? And then the list, lock, and cache structures each have a series of performance points that we need to be concerned with. And then the cost of duplexing, because I can tell you the cost of duplexing is typically twice the cost of not duplexing. When I say what the cost of duplexing is, what I'm talking about is host effect cost. So if I have a lock structure that every measurement interval, every 900 seconds, that lock structure consumes or causes, let's say 100 seconds of CPU on the ZOS system every 15 minutes, then if you're duplexing the structure, typically it'll be twice that amount, or 200 seconds of CPU. So there's a series of questions we want to ask ourselves. So I'm going to go into a few of those questions. I think I do 4 of those questions we're going to look at, just to give you a flavor of what's going on. Now, the next thing I'm going to do, just talk about real quickly in terms of looking at measurements, is not all measurements, but for typically when you're doing a coupling facility analysis, what's nice is when you have the data from all your ZOS systems combined together into one coupling facility report. Now, what happens with the coupling facility measurements is the measurements are actually divided up into two sets of measurements. You have software measurements and you have hardware measurements. The software measurements in the SMF74 subtype 4 record are measurements as seen by the ZOS system. Like, for example, how many requests were made to the coupling facility? System A is going to have that number, and it's probably going to be a different number than System B, which is probably going to be a different number in System C. So now I can figure out how many requests each system is making, and if I want to know the total number of requests being made, I can add those up together. But if one of those systems is missing, I'm going to miss that measurement, but just understand it's still going to tell me, if System C's measurements are missing, at least System A and B, I'm going to know its activity. That's the concept of software measurements. But in the SMF74 subtype 4 record, we also have hardware measurements. And the hardware measurements are actually gotten from the coupling facility itself. So an example of a hardware measurement might be, false contention for a coupling facility lock structure, right? And that's a measurement that is gotten from the coupling facility, or a cache structure is probably a better example, the number of directory reclaims, something that's happening in the structure itself. And so what happens there is you have that measurement, and if you have systems A, B, and C, and they are all collecting the same measurement, you don't want to add them together. You want each measurement, in other words, if we have, let's say cache structure, we have, 1 million directory reclaims, which I'm going to go through what that measurement is. But let's say you have 1 million directory reclaims. If I collect that measurement on systems A, B, and C, it's going to be exactly the same number because it's a hardware measurement, not a software measurement. And you never want to add those together. So just be aware of that when you are looking at coupling facility measurements, try to combine the measurements from all the systems into one coupling facility report. And if you're doing measurements and writing your own reports, make sure you understand the distinction between the software measurements and the hardware measurements. Software measurements are gotten from each ZOS system, and the hardware measurements are going to be the same for all systems because they're gotten from the hardware itself. That's what I want to say there. So let's talk about some of the questions I ask. And I think if you come to the class, I think there's like 100 questions. There's a lot of questions we like to ask. I'm just going to go through a few here. So one of the first questions I'm always interested in is how many requests are made to the coupling facility for each structure. In other words, let me just read it here. How many requests to the coupling facility is each structure responsible for? So in other words, we're going to have so many requests being made to the coupling facility. How much is being made by this XCF list structure? How much are being made to this lock structure, et cetera? And then we want to understand what the response times of those requests are. And we're going to want to understand what's called the synchronous response times and the asynchronous response times. So let me explain that. So as I said, if you look at the diagram on the bottom, you have the requester making the request to says makes the request to the coupling facility. You need a subchannel, you need a link, and then you have the coupling facility itself, and the request is going to be made, and you're going to have a response. When you have a synchronous request being made by the requester, now the requester is the one that says it should be synchronous, right? Something like DB2 knows that it wants its lock structures to be synchronous, or some other facility knows it wants its request to be synchronous. What's going to happen is the requester is going to make the request asynchronous. And what that means is that requester is not going to be able to do anything until a response is responding back to the requester. So in other words, the requester is on a processor. It makes the synchronous request. And while that synchronous request is going to says, is going to the subchannels, is going through the links, is going through the coupling facility, and all the way back, while all that's happening, the requester is holding a processor, basically spinning and consuming CPU seconds. So you can imagine if you have poor coupling facility response time, that's going to add to the number of seconds of CPU that are going to be consumed by this requester just sitting there waiting for a response back. And so that's why we're always interested in synchronous requests, because they are pure CPU consumption on the ZOS system. And you always want to be aware of that. Now, when the requester makes the request to says, it makes the synchronous request to the coupling facility. I'm going to talk in a moment how sometimes says will change that request to asynchronous, but let me go to what's called an asynchronous request first. An asynchronous request, again, is a request being made to the coupling facility, but now instead of being made synchronously, it's made asynchronously. Or another way of putting it is when the requester makes the request and the entire flow of the request is being processed, the requester is not sitting on a CPU waiting for a response. It's off doing something else. It freed up the CPU. Something else can be done. So although asynchronous requests have costs in terms of CPU, that cost is not due to spinning on the processor waiting for the request to come back. It's off doing something else. So again, asynchronous requests still cost CPU, but you're not spinning. So they tend to be less of an impact to overall CPU consumption on the machine. Now, what we always want to be aware of is what our response time of those requests are, and are you within the response time guidelines? Because if you're not within the response time guidelines, then typically what you're going to have to do is either do some tuning or at least understand why you're not within guidelines. Maybe you need to upgrade technology. Maybe you just need to accept the fact that you're getting large response times because your coupling facility is 10 kilometers away from your ZOS systems. Typically speaking, for synchronous requests, when we look at synchronous requests, we want that response time to be 5 to 20 milliseconds. In today's day and age, it's typically going to be towards the 5, 3, 2. I mean, you know, the technology has changed that these are going to be very small numbers for synchronous requests. Now, that might not seem like a lot, 5 microseconds, but 5 microseconds, when you're making millions of requests, do add up and do consume pure CPU and is measurable in MSUs. An asynchronous request, we have a little more leg room with. And typically for asynchronous requests, we're looking for 50 microseconds to 300 or lower, of course. Again, nowadays, you might get even lower than 50 microseconds. And we always want to be aware of the asynchronous request because, again, it could affect the response time of your transactions and whatnot. So we're going to look at these numbers. The reason there's a range in these numbers, like 5 to 20 or 50 to 300, is because you can imagine that some requests are very small. So when DB2 makes a lock request to the coupling facility, a lock request is less than, I think, 1,000 bytes, you know, what has to be transferred. So what happens is, you know, you're going to get a very low microsecond response time typically. But if you're transferring a chunk of data, maybe you're transferring several kilobytes of data, you can imagine that's going to take longer and more bandwidth to go across the links and the subchannels and whatnot. So as a result, you might get a larger response time, and that's something to be, aware of as well. Now, I will say that synchronous requests are very, very expensive. That's why we're always going to be interested in them. But I will say that sometimes what happens is a requester who makes the request to synchronous will sometimes change that synchronous request over to an asynchronous request. And it does that what we call heuristically. And all heuristically means is that it's a self-learning algorithm, or another way of putting it is SES is going to constantly be monitoring the response times of the request. And if those response times grow to a certain threshold value, it might then make the request from synchronous to asynchronous. Now that has a cost to it, and it definitely has an impact to performance, but at least you're not spinning on the CPU. You'll probably incur a larger response time on the request, but you're not spinning on the CPU. And if that response time goes down, then it'll start changing those requests, back from asynchronous to synchronous. It doesn't change the request, but it'll start making the request to synchronous again. So just know that you toggle between synchronous and asynchronous. So for certain structures, especially like lock structures, we're going to be interested in, are the requests being changed over to asynchronous? Because that says to us that the SES component of the operating system feels like performance isn't enough in order to get good response time. Now, I will say that if you're interested in what those values are, that it changes from synchronous to asynchronous, if you execute the dspace xcf couple command on your console, part of the display is going to look like this. And what this is telling us is what the threshold value is to make the request. So simplex and duplex is just that. Simplex means it's not a duplex structure. Duplex does. The first two numbers are for list and cache structures. And the last two numbers are for lock structures if you're duplex in the lock structure or not duplex in the lock structure. And these threshold values here are in microseconds. On the right-hand side here, it tells you where this default value came from. It could come from PalmLive because you can specify this in your PalmLive members. It can come from the operating system, or it could be heuristically adjusted. So the point being is it's either the default, or you're changing it, or it's heuristically being changed. So for example, in this case, these are all the default values. So 26 microseconds. But I happen to know that sometimes if it changes it, it'll say, hey, the system changed it. You're not using the default anymore, and this is the new value. And that's an interesting exercise to go through as well. So this is where you're going to want to understand, when your flip point is for converting synchronous to asynchronous. So what we're going to do is we're going to use the CMF or RMF subchannel activity report in our product Pivotal. Of course, we have lots of reports like this as well, just more intelligently reported on. But what we're looking at on this particular slide is what the CMF and RMF report look like when measuring coupling facility synchronous and asynchronous response time. Now, I will say that on a per structure, per system basis, all the numbers are given to us. What this is here on this particular presentation, on this particular slide, is the total number of requests being made by each system. How many requests did system 0 make? How many requests did system 1 make? In other areas, we get all of these numbers we're looking at, we're going to get them broken down by structure. So just know that this is just the highest level we report these measurements, but you do get them by structure eventually. And so what we're looking at here is, let me just change the pointer option here. We're looking at here, for example, is we're saying how many requests were made from system 1 to this coupling facility, right? And the number of requests being made is basically about, what is that, 927,000 for system 1. And then you get the request per subsystem, per second. I'm not going to go through any of these other measurements here, but in context of this particular presentation, what I just talked about is what we do get is, of those requests being made, how many are synchronous and how many are asynchronous? So in this particular case, we made 595,000 as synchronous, and we made 323,000 as asynchronous. If you add these two numbers up together, it could be pretty close to this number here. Understand that it may not always equal, because what happens is there is batching, what we call batching of requests. So sometimes SES will batch the requests together, and then there'll be fewer requests being made to the coupling facility. But just understand it should be pretty close. And then SES also makes its own request. The next thing we have is what the response time of these requests are. So here's an example where I have on system 1, I'm making 595,000 synchronous requests, and they're getting an average of 22 microsecond response time, which is slightly above what our guideline is. Again, typically you're going to see these down in the 5 microsecond ranges. And then for asynchronous, you're going to have this many requests, which now have a 94 microsecond response time, which is within our range. And again, if you're not happy with that response time, you want to understand who's making those requests, those numbers are broken out by structure eventually. So this is a quick way of looking at our response time. This is like the first thing I actually do whenever I look at a coupling facility report, is to kind of see what kind of response times the requests are getting. Changed here doesn't mean that it was changed from synchronous to asynchronous. What it means is you encountered a subchannel busy, it was a synchronous request and was changed to asynchronous. It's not what we call our heuristic algorithm changes, which I'll explain later. I think, and I just went through all this, so I just wanted to talk about this. This is an example now of what the report looks like for an individual structure. So let's go back to system 1. System 1 made this many requests to the coupling facility for this lock structure, this DB2 lock structure. So this is now a breakdown of this number of requests to this coupling facility, but only for this one structure. And what we get here is, of the request, we want to know how many are synchronous and asynchronous, and this is for this one structure now. And then we want to understand the response time of those requests. So now we know that, the lock structure, which typically should, in today's day and age, have like 5 microseconds or less response time, this tends to be a little bit of a problem because this guy has a 20 microsecond response time. And again, remember, during this response time, the CPU is actually spinning. So technically speaking, if I multiply the 20 microsecond response time to 150,000 requests, just do the math, and you can see how many CPU seconds that is actually costing the ZOS system. So the way you look at this graphically, this is an example of a Pivotal report. So here's an example of, all right, I have some number of synchronous requests. What was the average response time of the synchronous request for this? In this case, it's an ISG lock structure by these systems here. And we see here that we're getting response times of about 6 or 7 microseconds, which is within our guideline. And this is kind of what you want to look at for each individual structure. Am I within the guidelines? And if not, why? So if I look at the next slide, here's an example of an ISG lock structure from a different environment. And what's interesting on this one is notice that for this one structure on some systems, like in this case, system D, we're getting really good response times. And on these other systems, we're getting in the just between 35 and 40 microseconds, which is well outside our guideline. And you can see how that compares to the response time being achieved by system D. Why would this happen? It typically is due to distance. I'm not saying this is I happen to know that in this case, it is due to distance, but you have to look at all reasons, but distance is a big one. In this particular environment, I happen to know that the coupling facility is some number of kilometers away from the exploiting ZOS system. And as a result, it's going to take time to put those requests over the link because speed of light, although super, super fast, it does still have a limit to it. So it is going to incur a response time delay. So this is just an example of looking at response times between a coupling facility where the ZOS system is right next to it versus a coupling facility where it's some number of kilometers away. Now, that's an example of looking at requests. There's a lot of other questions we can ask, but as I said, for this particular presentation, what I kind of do is make it a little bit rounded to look at different areas. So let me ask another questions in a completely different area. So now we know about response times. Let's talk about what percentage of lock requests are resulting in false contention. And hopefully this discussion will give you some understanding of lock structures in addition to understanding false contention and measurement of false contention. So before we talk about false contention, let's talk about the two types of lock structure contention events. So actually there's more than two, but there's two primary contention events. The first contention event that we can have on a lock structure is what we call a real, I'm sorry, I lost my cursor here, is a real lock structure contention. Now what happens here is in the lock structure, you have what's called the lock table. And think of a lock table as being an array of, many, many different entries. It's basically a bit array of many entries, typically millions of entries. And those entries are used for serialization of a request. The second part of a lock structure has information about the request. It's not the resource itself, but information about the resource and information about the users that want to make the request. So for example, here, let's say I have a resource called ABC. It could be a page of DB2, a DB2 buffer pool page or something like that. You have a resource called ABC. That's the resource. And then what I have is another part of the structure is information about each one of the users that are making a request or have interest in this resource ABC. So in this particular case, what I know from this particular diagram is I have a resource called ABC. User 3 is holding it exclusively, and user 1 and 2 want it in a shared state. So naturally, you can't have one guy be exclusive and the other guys be shared. So that becomes a contention event. And this is what we call a true contention event. One guy has it exclusive, the other guys want it shared. And you can't have both. So you have to kind of serialize the thing. But what happens here is we have information about this request in the coupling facility entry here. So entry number 2 represents ABC. So if another requester came in and wanted to look at ABC, it's this entry 2 that tells them that this request is, this resource is being held. So this is telling us the resource is being held. It's being held by user 3. The other 2 want it shared, and it's for resource ABC. This is what we call a true contention event. Now, the thing about true contention events is it's typically due to, it could be due to the fact that the database is not well designed, that maybe, everybody is going against the same exact piece of data. Maybe the person who designed the application or the database has a particular row that everybody needs to update or look at. And as a result, everybody's pounding against it. That's an example of poor performance. Or it could be because the link technology or the distance is so long that as a result, user 3 in this case is holding the request so much longer than normal, and it's causing contention. Regardless, those are performance points that need to be looked at, but typically real contention is a function of the database, of the application, and of the technology being used to make the request. And of course, the workload itself. How many people, is it a really intense data sharing workload, or is it just, a workload that nobody really is going against the same sets of data as each other. All those are contributing to real contention events. But then you have a concept, what we call false contention event. And false contention is just what I'm saying. It's a contention event that appears like a contention event, but in reality, it's a false contention, meaning it's not real. It's not a real contention. So what we're looking at on this particular slide, I'm trying to demonstrate, is we have a resource called ABC and users 1 and 2, 1 and exclusive. So they get entry number 2 for that request. Along comes a requester, user 3 in this case, requesting XYZ. And then when coupling facility goes to assign a lock table entry to it, it happens to pick the same lock entry table as ABC. You know, what the coupling facility doesn't do is it doesn't look for the next available entry, or doesn't look to see if that entry is occupied already. And the reason it doesn't do that is for performance points. We're talking about lock structures that we need super fast performance on. So why check? I'd rather take my chances to figure out if I have a false contention event. But false contention does have performance price to it. So we want to minimize those. So in this particular case, it doesn't matter who, but let's say request to user 3 now is going to be delayed because ABC is used, because user 1 and 2 are using resource ABC against, and it happens to hash to the same lock entry. So here user 3 is going to be delayed by users 1 and 2, but both users, or user 3 is interested in a completely different set of resources than user 1. It's false. It's a false contention. And what happens in this particular case, the coupling facility recognizes it as a contention event, just like it does for the true contention. Whether it be true contention or false contention, the coupling facility never resolves the contention event. Instead, what happens for both type of requests is that the coupling facility goes back and which then messages the requester to say, hey, you have a contention event going on here. Something's going on. I can't do anything until you tell me, until you resolve this contention event. So what happens for both real and false contention events is, let's say DB2 is an example. The DB2s will start waking up and saying, oh, there's a contention event going on. And then what it does is it starts sending XCF messages around the sysplex to try to resolve the contention event. So when I say there's a false or real contention event, and it's supposed to be especially when it's a synchronous request, during that period of time, all the DB2s in this particular example are messaging each other. You'll see messages go around the sysplex. If you ever look at XCF, you'll see XCF, you'll see a XCF group called IXCLO and then some number. That's what's happening here. It's sending messages all around. In the case for true contention, it'll send all these messages around, and eventually the DB2s will coordinate what's going to happen with that request, which is goodness. Again, it all takes time. But for false contention, what's going to happen is all the DB2s are going to wake up. There's going to be all this messaging going on. There's going to be all these delays going on just for the DB2s to talk to one another to figure out, oh, this is ABC, this is XYZ, this is really not a contention event. You can go ahead and do what you need to do. And that takes time. That is a performance impact. So naturally, we want to alleviate or mitigate as many false contention events as possible because they are true performance overhead. So how can we do that? What do we do to measure that? So this slide just talks more about, what true contention is versus false contention. So take a look at the slide when you can. The way we measure this in the CMF and RMF reports is for the particular structure itself. So here we're looking at the lock structure on this particular coupling facility. And what we want when we're looking at true contention, when you're monitoring true contention, the good guideline that we use is we want less than 5% of our contention events to be true contention events. In other words, we want less than, of all the requests being made to the coupling facility for this lock structure, we want less than 5% to be due to contention, due to true contention or any contention in this matter. So looking at this particular chart for this one structure, let's say for system A, we know the number of requests being made by says. This is the request being made by says. Over here on the right, we have additional numbers. Request total here, if you notice, is a larger number than the number of requests here on the left. The reason is that request total is the total number of requests being made by this requester, this DB2, to the lock structure. That's the number of requests being made. And as I said, says takes those requests and sometimes batches them up together to make fewer requests to the coupling facility. And that's why this number on the left is typically smaller than this number on the right. So the number on the right rather, is the total number of requests we made. The next number we have here is how many of those requests are deferred. What deferred means is that the coupling facility says, hey, something's going on here. I can't really do anything. You guys got to go resolve this event. I don't know what it is, but you got to resolve it. So it defers the request. And then the next number is how many of those requests that were deferred was due to some contention event, whether it be true contention or false contention. What number was due to a contention event? And we see, even though these numbers are rounded, they're pretty much the same number. The final number we have is how many of those actually resulted in false contention. So the contention event number that we give here, the 67,000, includes both real contention plus false contention. So the false contention is just false contention. So naturally, if we delta these two numbers against each other, then we now know that there's, 51,000 false, real contention events versus 16,000 false contention events. And so we want to make sure that the contention event number here, the 67,000, is less than 5% of the request being made to the coupling facility. So it's 5% of this number. That's our math that we want to do. If you want to calculate it, go do it. The next thing we want to understand is the false contention. And we recommend less than half of 1%, less than 0.5% of requests result in false contention. So again, if you look at the numbers here we have the number of requests totally, number of requests made total, and then here we have our false contention number. We want to make sure the false contention number is less than that, into less than half of 1%. A couple of things I want to point out is that you will always have false contention. So always going to have false contention. So we want it to be less than half of 1%. If you find yourself above that threshold, you're going to have to do some tuning. And typically the tuning you do for false contention is you have to increase the size of the structure. Real contention, you have to kind of do things to the application, to the environment, to the database, to maybe change the workload. I don't know, just there's things you have to do, but they're not due to the size of the structure. Size of the structure, if you make larger, will alleviate false contention. But even if you make it really super large, you're still going to have some false contention. So we want to make sure it's just less than half of 1%. That's the guideline. So here's a chart of looking at how many requests are being, the percentage of requests being deferred by the coupling facility. So this is our 5% guideline number. So here we have our guideline is 5%. And we want to know what percentage was made for the ISG lock structure across all these systems here to the coupling facility. And we notice here that less than 5% have contention events. Again, if you see this number is high, look at your false contention to see if that's the reason it's high. If not, and it's really high, I mean, the example I was going to put in here, but I took out, was a really high true contention event example. But the point is there, you have to tune the environment in the database and whatnot. So here we're within the 5% guideline. The next thing we like to look at is in this particular environment, and this is the same environment, if I remember correctly, right? It's the same environment. For the ISG lock structure here, although we're within guidelines for contention events, we want to look now is we want to zero in on false contention events, and we want that to be less than 0.5% of all requests. And we see here that we're above that number here. So this is a good example of this coupling facility structure is probably too small, that we need to make sure that we make it larger. And what that making it larger does is it increases the size of the lock table. And by increasing the size of the lock table, thus you decrease or can alleviate false contention. The thing I wanted to point out on this particular slide, and this is for the previous example I just gave you on the previous two slides, is what we're looking at here is on the axis here, the green line here is how many entries we have on our lock table. And I don't know what it is, but it's like 2.1 million entries. That's, a lot of entries. And down here, what we have is the orange line, which you really can't see here, but there's an orange line which says what percentage of requests are actually what's the number of requests that are actually in use? And you can see here that even though we have millions of requests, millions of entries defined, we have a very small number that are actually in use. In fact, if we look at the percentage in use, you can see the percentage is quite a small number. So even though the vast majority of the entries are free, we still get false contention. And even then we're above our contention event, our 0.5%. So these are the numbers you need to be aware of, that I could tell you that this coupling facility structure needs to be increased in size. The thing I just want to point out here, and I just want to back up a slide, is whenever you increase the size of a structure, always make it a power of 2 plus some. Power of 2 plus some. In this particular example, I think this particular customer had it as, I forget what it was. Let's just make up an example. Let's say the size of the structure was 64 megabytes. Well, it's got to be a power of 2, which 64 megabytes is, but it's got to be plus some. And when it's not plus some, when I say plus some, add another 5, 10 megabytes to it. What happens is we want that power of 2 number to be the size of the lock table. So what's happening in this particular example is, let's say again, that the size of the structure was 64K. In reality, the coupling facility lock entry table is really only a 32K locked entry table because it needs all that other area of memory for some other reasons. So just understand, always a power of 2 plus some. I can go into that much more detail in the class if you ever go to the class, or send me an email and I'll certainly answer that question. Okay. And as I said, I wanted to kind of do this rounded presentation. I think this is the last kind of area that I want to talk about, but this is a really interesting area. And the question here is going to look at something to do with cache structures. So we looked at response times, we looked at number of requests, we looked at lock structures, false and real contention, and how to monitor that. What I want to do here is look at cache structures. And to do that, let's ask the question, are there any cross invalidates due to directory reclaims, right? Now, in a vSAM RLS environment, you're going to expect to have directory entry reclaims. In a DB2 group buffer pool environment, which many of you are, you want to make sure, unless there's some sort of batch job running that's causing it, but in terms of your workload, we want to make sure that the directory reclaims are 0 or super, super close to 0. So the question is, what the heck is a directory entry reclaim? So let's talk about that. So to talk about directory entry reclaims, let me change my cursor over to a pen. To talk about directory entry reclaims, we kind of have to understand some of the concepts of a cache structure. Now, a cache structure, I'm not going to go into all of it here because it's usually a much longer lecture to explain cache structures and how they work and how they're used for data sharing and whatnot. But let me give you, hopefully not, high cursory overview of a cache structure. When you have a cache structure, when you define a cache structure, in this case, let's keep it as a DB2 cache structure, a DB2 group buffer pool structure, just for mindset purposes. When you define a structure, there's different areas that we're always interested in. Now, first, the reason you're defining a structure in the coupling facility is because you have a DB2 on your ZOS systems, and the DB2 is reading data into the local storage. And always remember that local storage is where you want your data to be. You're never going to get better performance than having the data in memory on the ZOS system for DB2. So you're going to have that. Then what happens is you define the cache structure, and the cache structure is going to have what's called a directory, which I'm listing here, which is the directory, and it's going to have a data entry area. What the data entry area is, we're not going to talk about it here that much, but what the data entry area is if you want to cache data into the coupling facility, then that's the cache data. That's what the data entry is used for. So that way, if you need to read the data in or reread the data in, or some other ZOS system already read the data in, you're going to get much better performance if you read that data from the coupling facility than if you have to go out to disk to get that data. So that's think of this as the cache area of the store of the coupling facility. But the way data sharing works, the magic is in the directory portion of the structure. And what the directory portion of the structure is, it's where the coupling facility keeps track of which systems have interest in which pieces of data. Okay, so in this particular case, we have system A that read data ABC in, right? And it's going to take a directory entry and says, hey, look, I read ABC in, I have interest in ABC. System B in this case happens to read ABC in as well, right? So it reads ABC in as well. So it goes to that entry and says, oh, look, I also have interest in ABC, right? So they both now have interest in ABC, and the coupling facility knows that. Now, if system A goes along and is referencing the data, and system B is going along and is referencing the data and never changing it, everything's fine. Everything's perfectly fine. So in this particular case, they each have a valid version of the data. Okay. But what happens many times is the data can be changed. So let's say in this particular case, system B wants to change the data. And I call that ABC prime. So that's what the prime is about, right? It wants to change the data. So in other words, it wants to update the data ABC. So to do that, it has to get the lock structure. It has to get, it has to get the lock entry. So it has to do some serialization. So that's all we kind of talked about before. But once it has the lock structure and is holding the lock exclusive, it can change the data. The problem is that once it changes the data, that means the buffer on system A that contains the same piece of data is no longer valid because system B made an update. So system A is going to have an old version of the data. And again, this is the magic of the directory portion of the structure. When system B goes to update the data, it updates the data. It can optionally write the data to the coupling facility. So that's where the cache structure portion comes in. But what's going to happen is it's going to look at the directory and say, oh, look, system A also has interest in the data. So what I'm going to do is I'm going to invalidate the data in the group buffer pool. I'm going to invalidate the data in the local buffer. And what it's happening here is it's also updating this vector table that exists in the hardware area of memory for system A. And what it's doing with this vector table is it's telling system A, your data is invalid. Okay, your data is invalid. Okay, if system A never looks at the data again, who cares? It has an invalid version of the data. It never looks at it again. It doesn't care about that data. So who cares if the data is invalid? But as soon as system A goes to look at that data again, what it always does whenever it looks at data is always checks the vector table and says, do I have the most up-to-date version of the data? Before, when system B was doing it, it had the most up-to-date version, so it passed the test. In this particular case, if system A looks at the vector table, it's going to see that its local data is invalid, right? And what it now can do is it says, oh, look, I have an invalid version of the data. Let me reread the data in. It always goes up to the coupling facility first to see if the data is there. If it is, it reads it in from there. So now this data can be updated from the coupling facility version. If it isn't in the coupling facility, then it's going to go out to disk and read it in from disk. The point is, it was the directory portion of the structure that actually caused it to recognize that it had an old version of the data. And it's this directory version of the data that I'm interested in for this particular question. The problem comes in is you have this concept called directory reclaims. And what a directory reclaim is this. Now, we mentioned that directory is used to understand if you have the most up-to-date version of the data. What can happen is system B reads data ABC in, and it has, it has the version there, fine. And what's happening is, I'm sorry, let me rephrase that. System A read data XYZ in, and it has an entry in the directory. I'm sorry, it has an entry in the directory. And then time goes by, some time goes by. System B comes in and reads record ABC in. So it says, all right, I'm reading ABC in. Let me go write my directory entry to say that I have interest in ABC. But when it goes to do that, all the entries are occupied. All of them are occupied because this is a finite control block. It could be all the entries are occupied. System B comes in, says, I have interest in ABC, and coupling facility says, sorry, I can't help you because all the entries are occupied. Well, he doesn't really say, sorry, I can't help you. What he actually does, the coupling facility, is it actually goes through and looks at the oldest entries in the directory that says, look, this data hasn't been referenced in a while. Let me free these entries up for system B. So to do that, it goes out and says, which data entries are old? Oh, look, the one for XYZ is old. So I'm going to invalidate that, and I'm going to say that it's invalidated in the vector table. The thing is, XYZ is not an old piece of data. It's a perfectly legitimate, good piece of data. But now what we're doing is we're invalidating it. So if system A ever comes in again and wants to reference XYZ, it's going to recognize as its local buffer as being invalid. So what happens is it's got to either reread the data in from the coupling facility or reread it in from disk, and that's a performance overhead. That should not be happening for coupling facility structures. So this is just going over different reasons for cross invalidates. Real quickly to end the presentation, let me just say that we're going to look at this report here. And what we look at the report, what we're looking at here, just let me go back to the pointer options, is for each structure, we want to understand the number of requests being made, but we also want to understand the number of directory reclaims that are being made due to cross invalidates. We want these numbers to be 0 for directory reclaims. You don't want to invalidate local buffers just because you made the directory too small for your structure. So here's another way of looking at it. Here we're doing it for one particular structure. We're doing it for this particular DB2 structure. We see for system A and B, but this is an example of a hardware measurement because these measurements come out of the coupling facility. So that's why there's one set of measurements for all systems, but we see these cross invalidate numbers. A lot of those cross invalidate numbers are actually due to cross invalidate due to directory reclaims. From a measurement point of view, what I do is in Pivoter, what we do is we look at we have a report that says directory reclaims, directory entry reclaim count, which should be 0 for DB2 group buffer pool structures during regular activity. So we see here for this particular DB2 group buffer pool 2, we have some number of, hundreds of thousands of these directory entry reclaims over 24 hours. This is what we don't want to see. But when I say we don't want to see it, I want to say that what happens is there are times that you're running batch reports. I'm sorry, not batch reports, batch jobs to maybe reorganize a database or whatever. You're doing something to the database. And as a result, you're slamming, let's say you're reconciling accounts if you're a bank, you're slamming the database. And as a result, you're going to have lots of directory entry reclaims. Now, I'm not interested in this case. The case I'm interested in is like this, where I have this particular cache structure. I see lots of directory entry reclaims, and I see that they're happening on a regular basis. This is an example of the structure being too small. And then what we look at is we say, well, how many entries do we actually have? And notice how this is pretty much flatlining. And that means that this particular group buffer pool has this many entries in the structure that maybe if we increase the size of the structure, we're going to have less directory entry reclaims. You don't want directory entry reclaims because it's such a small part of the structure that to make it bigger, to make the structure bigger is probably going to benefit you from a performance point of view. That was my presentation on looking at coupling facility measurements, tuning, and measurement and tuning tips. Hope you enjoyed that. I don't see we have any questions in the chat, but always feel free to send me questions. I'll be happy to answer them. Hopefully you saw that it's a big topic. We're teaching a class on it, but it's a big topic. Just understand, be aware of the fact that in this particular presentation, you want to look at your response times of request, asynchronous versus synchronous, and if those requests are being changed heuristically. So look at the response time and the number of requests being made of each. You want to look at your lock structures to make sure you have an acceptable number of contention events and false contention events. And then finally, hopefully I showed you the concept of cache structure, directory entries, and directory entry reclaims. And we want those to be 0 on a regular basis while your workload is running. You want that to be 0 for DB2 group buffer pools. If you see a spike for one interval, that usually means you're running some batch job. We're talking about regular activity. It is a drag on performance and your coupling facility response times. Do we have any questions? I only have 2 minutes left.
Yeah, thanks, Peter. I don't think we've got any questions in at the moment, but just as a reminder, please do feel free to type away in the chat box if you've got any questions.
And if you want to see these reports, with your measurements, feel free to send us data. That's what I'm saying here on this particular presentation. What we do is if you send us a group of SMF data, we'll produce lots and lots of reports for you, and then we'll have a phone call with you to explain the reports and to kind of give you some hints and tips based on the measurements we see. It's a good way for us to know you and get introduced to you, a good way for you to introduce yourselves to us. And I promise you, the bulk of the session is analysis. We'll give you measurement hints and tips. So feel free to send us some SMF data. Just send me an email, and I'll explain how to do it. But I'd love to hear from you. I hope you enjoyed the presentation and the QR code. Oh, I thought I had the QR code on my last slide, but the QR code's on the header slide of this particular presentation. And as we see, the link is placed in the chat box for feedback. So that's it from me. Thank you.
Okay, yeah, still no questions. Thank you so much, Peter. Really appreciate your time. If you do have any questions for Peter, you can see Peter's email up on the screen, so do feel free to get in touch.
Always feel free to contact me. Thank you.
Perfect. Well, I think we can close it there then, and we'll be back in here in half an hour.
All right.
Thank you once
Enjoy,
again, Peter.
everybody. Thank you. Bye-bye.
Bye-bye.